Good morning and welcome back to our NPTEL lecture series on classics in total synthesis part 1. So, we have been discussing total synthesis of triquinanes, and in the last week we talked about total synthesis of triquinanes using photochemical reaction, for example Paterno-Bucchi reaction as a key reaction to form triquinanes reported by Virey-Schravel's group. So, we will continue our discussion on total synthesis of triquinanes, where photochemical reactions have been used as the key reaction. Okay. So, today we will talk about maybe 4 or 5 total synthesis, and the first one which we will discuss is the total synthesis of sulfy-perfol 6-ene 5-one, and this synthesis, particular synthesis, was reported by Demuth and Hinsken, and interestingly what they have used is an oxo-dipymethane rearrangement induced by photochemical condition. And overall, if you look at the whole synthesis, though the number of steps are little bit more, the strategy of using oxo-dipymethane rearrangement to get the triquinane is a unique one, and the starting material, that is the diene, which is required for the asymmetric Diels-Hall reaction, was started from chiral enone, which we will discuss. From the retrosynthetic point of view, this natural product can be obtained from this particular compound. You can see what one has to do is 2 methyl groups as well as the double bond should be introduced. That can be done by first introducing a double bond here, then you add a methyl group followed by quench with methyl iodide, then introduce a double bond. So, one can do it in 3 to 4 steps, and this ketone can be obtained from another ketone. And why this ketone was introduced, you will know, that is because for the photochemical oxo-dipymethane rearrangement this ketone is required, and before that this ketone should be reduced and protected, and this particular ketone can be obtained from this tetracyclic compound. Okay, see, now you can see a cyclopropane. Okay, so this is formed through the oxo-dipymethane rearrangement, and reductive opening of this cyclopropane followed by quenching with methyl iodide, you will get this intermediate. Okay, and the key reaction here is the oxo-dipymethane rearrangement of this tricyclic compound. And when you look at this tricyclic compound, as you know, it can be obtained from a 4+2 cycloaddition reaction, wherein this is the diene. Okay. This diene can be obtained from a commercially available compound, as well as one can make this in large quantity from Hages-Parrish ketone, and that is nothing but if you have this, instead of alcohol, if you have ketone, that is Hages-Parrish ketone, and that can be obtained from 2-methyl cyclopentane 1,3-dione using L-proline as the catalyst. One can do a Michael addition followed by aldol reactions, which we normally call it as a Robinson annihilation sequence. Okay. So, the starting material for this is 2-methyl cyclopentane 1,3-dione, which is commercially available. So, before we go into the details of the total synthesis reported by Martin Demuth, we will discuss the key reaction, which is oxo-dipymethane rearrangement. So, what is that? So, if you have a system like this, that is, you can call it as allyl ketone. Now, under photochemical condition, first this carbonyl will form a diradical, same thing will happen with the double bond. So, that can lead to the formation of this type of cyclopropane. Assume that this is CH2. Okay. So, this right diradical, what will happen next? It will open up. So, how it will open up? So, they will open up like this, and it will lead to the formation of original ketone. Ketone we started with, you will get the ketone back, as well the resultant diradical. Now, you can see here, this is a radical, this is a radical. They will combine to form the cyclopropane. Assume that this is CH2. Okay. So, basically if you do an oxo-dipymethane rearrangement, you can see the formation of cyclopropane. Okay. And this one can do on bicyclic system, tricyclic system, and here is an example where you have a bicyclic system. So, that will give like this tetra radical, and then what will happen, this tetra radical immediately you can see it will form a cyclopropane. Okay. Then this radical on the oxygen will come back and then open this cyclopropane to give this bicyclic diradical. This bicyclic diradical one can easily redraw like this. Okay. You can see here this is 1, this is 2, this is 4, this is 5. So, that is a 5-membered ring and the remaining is 6-membered ring. Now, these two diradical will combine to form the tricyclic compound, in that the third ring is a cyclopropane. So, this is the oxo-dipymethane rearranged product. Okay, this can be easily obtained from any bicyclic compound having a carbonyl and double bond at appropriate place. When you do that, one can also expect another product which is normally minor product, that is arising out of 1,3 acyl shift. That is, when you do a photochemical reaction on this ketone, first Norris type 1 cleavage will take place, where you generate this diradical, followed by migration of the double bond. Okay, the double bond will migrate and you will get the corresponding allyl radical. Okay, what will happen? Now this will migrate, or here you can write like this, and these diradical will combine to form cyclobutanol. Okay. So, one can see using oxo-dipymethane rearrangement you can get a cyclopropane, or if you use 1,3 acyl shift, then you will get a cyclobutanol. Okay, 6-membered ring fused with cyclobutanol. Now, let us see how Demuth synthesized this natural product. He started with 2-methylcyclopentane 1,3-dione, which we saw during the retrosynthetic analysis. Then using the Robinson annihilation sequence, first Michael addition with methyl vinyl ketone, followed by treatment with S-proline and dehydration, you get the Hedges-Parrish ketone. Okay. You have an enone and a ketone, and the ketone can be selectively reduced with 0.25 equivalents of sodium borohydride in ethanol at 0 degrees to get this alcohol. And once you have this alcohol, then you can protect this alcohol as mom ether. Okay. And if you treat with LDA TMS chloride, so it will generate anion here and then it will form an enolate. That enolate will become enol TMS, and this is the diene. Now he did Diels-Hall reaction with maleic anhydride to form this tetracyclic compound. Okay. So, this is the intermediate, and this intermediate you can see this is a transition state. Okay. This is a transition state, and this gives this tetracyclic compound. Now, this anhydride, if you look at this anhydride, should be converted into double bond. So, he used a electrolysis method, like hydrolysis followed by di-decarboxylation to give the double bond, and this is the key precursor for the oxo-dipymethane rearrangement. So, taking this compound and then shine light, it undergoes oxo-dipymethane rearrangement, and as I mentioned earlier about how oxo-dipymethane rearrangement takes place, first it will form this tetraradical and followed by formation of the cyclopropane and opening of this 3-membered ring, you will get another diradical, and whereas this will be a carbonyl group, and once you have this diradical, and you can number it, for better understanding, always better you number the starting material. Okay, you give numbering. So, the 6-membered ring you can give numbering and then see where the radicals are in the starting material and when you redraw the structure for better understanding, you can give the number and then you can easily make out where these two radicals are. Once these two radicals you can write, and that will form the corresponding cyclopropane. Now, as I said, there is a possibility of forming 1,3-acyl shift also. Of course, the yield is only 5% and the main product is only the required one, that is the cyclopropane formation. So, this tetracyclic compound next is reductively opened. Okay, so lithium diisopropyl amine and TMS chloride. So, what happens? This will be cleaved, this cyclopropane will be cleaved, and then it will form the corresponding enol TMS. Okay, this will form the corresponding enol TMS, because you are using lithium diisopropyl amine and quenching with TMS chloride, because that enolate, once it is generated, you trap that enolate with the corresponding TMS chloride. Once you have that, that is the first step, and the second step, the enol TMS ether can be cleaved with any fluoride source. So, that is what they have done. They have done with this benzyl trimethyl ammonium fluoride to cleave the enol TMS to generate the O minus, and that O minus you quench with methyl iodide. Okay, you quench with methyl iodide, you stereoselectively introduce the methyl group. Okay. So, now if you count the number of carbon atoms, you will see here in this ring you have 6, here you have 2, 8, and then here you have 3, and then here you have 1. Okay. Next step is to remove the carbonyl group. So, you do not want the carbonyl group. Okay. This can be done in many ways, but what they have done is they have protected the ketone as dithiazide derivative. Okay. Then you remove the MOM group. Okay, you remove the MOM group is using titanium tetrachloride, you get the hydroxyl group. At this point, you can remove the dithiazide using a combination of titanium tetrachloride, Lewis acid, and a reducing agent. So, they use titanium tetrachloride and lithium aluminum hydride to get the corresponding CH2. So, the deoxygenation of carbonyl group was done in 2 steps. First, you protect the dithiazide, then remove that with titanium tetrachloride and LiH. Now, what you need to do, you have to oxidize the alcohol to ketone. Okay. Then you have to introduce the 2 methyl groups and then double bond. So, here you use some expensive reagent. So, first you treat it with LDA TMS chloride, which you know it will form the corresponding enol TMS. Then for introducing the double bond, you use DDQ and this exotic reagent, which looks like exotic reagent, but it is not. It is a reagent derived from trifluoroacetamide. Okay, take trifluoroacetamide and then you treat with trimethylsilyl chloride, you get this. So, this is the reagent, you know, you can get a double bond, or you can introduce a double bond next to the ketone. Next, you have to introduce 2 more methyl groups, one here and one here, but at the same time the double bond should be kept intact. So, how it can be done? First, you add the 1,4 addition on the double bond with lithium dimethyl cuprate and quench the enolate with methyl iodide to get the 2 methyl groups, and then repeat the same process, So, that is, you introduce a double bond via enol TMS followed by oxidation to get the natural product. Okay. So, that way if you look at this synthesis, the key step in the synthesis was the oxo-dipymethane rearrangement, and they started from commercially available 2-methylcyclopentane 1,3-dione, and then they use Robinson annulation as a key step to make the next starting material, that is azosparic ketone, and overall this total synthesis was accomplished in 11 longest linear steps with an overall yield of 1.6% yield. So, now we will move to another very short total synthesis reported by Uehara. Okay. Here again, as I said, we will be discussing only the photochemical reaction which has been used as the key reaction in the synthesis of triquinanes. And what he has used in this particular synthesis is photochemical 1,3 acyl shift. In the earlier synthesis which we saw, where oxo-dipymethane rearrangement as the key reaction, and there also he got 1,3 acyl shift product as a minor product. In this particular case, Viagra has used photochemical 1,3 acyl shift as the key step, and that is a main reaction to get the key starting material or key intermediate. So, let us see his retrosynthesis, and when you look at this capnylene, as I said, whenever you have a functional group or if you do not have many functional groups, you can introduce a functional group. Okay. So, here you have a functional group, a double bond, but that may not be sufficient sometimes when you do a proper retrosynthetic analysis. So, it is better to introduce another functional group which can facilitate the retrosynthesis to get a simpler starting material. So, that is how what Viagra has done, he has introduced a carbonyl group at the middle ring. The idea is, if you introduce a carbonyl group, then one can do an intramolecular alkylation. Okay, so that is what he planned. So you can see, you can if you make this as a good leaving group, okay, if you make this as a good leaving group, then you can generate anion and you can form the third 5-membered ring, isn't it? So that was the idea. So for introducing the carbonyl group, then you can introduce a double bond here. The reason for introducing the double bond is this 4 carbon unit can be added stereoselectively using a 1,4 addition reaction. And now if you look at this, you reduce this double bond and introduce a double bond here. What for? That is how he can use the photochemical reaction, that is 1,3 acyl shift, to get this compound. Let us see how he made this compound in the real synthesis and how from there he used the 1,3 acyl shift to get this bicyclic compound. The total synthesis started with metacresol methyl ether, metal ammonia reduction gave the diene, and you treat with sodamide. When you treat with sodamide, then it will generate an anion and the migration of the double bond will take place to give this type of diene, or you can this will give this type of diene, but this is the most stable diene. So, you get this diene and this can undergo Diels-Sal reaction with alpha chloroacrylonitrile. Alpha chloroacrylonitrile is a synthetic equivalent for ketene. Okay, so ketenes normally cannot undergo 4+2 cycloaddition reaction. So, that is why indirectly you have to use some equivalent which can give ketene in the product. So, alpha chloroacrylonitrile is one of the best synthetic equivalents for ketene. So, you do the Diels-Sal reaction with alpha chloroacrylonitrile. Now, if you treat with potassium hydroxide and DMSO, that will hydrolyze this to ketone. Okay, try to write mechanism for this. Okay, so mechanism for the hydrolysis of chloro-nitrile adduct to the ketone. It is a very interesting mechanism. Take this bicyclic ketone and then treat with potassium tertiary butoxide, excess potassium tertiary butoxide and methyl iodide. You can introduce 2 methyl groups next to the ketone. Okay. Then when you reduce this with sodium borohydride or lithium aluminum hydride, you get a mixture of endo and exo alcohol. So, this is endo and this is exo alcohol. So, almost you get 1:1 ratio. These two will give 2 different products upon treatment with acids. For example, if you take this endo alcohol, so first it will protonate the hydroxyl group and that will be a leaving group. Now, the bond which is anti to the leaving group. So, this is the bond which is anti to the leaving group, that is the OH bond, and this is the bond which is anti to that. Okay, that will migrate, and what will you get if you use Lewis acid is, okay, you will get this product. So this is nothing but, if you look at, you can write like this. That is because the this CC bond, which is anti to the leaving group, migrates. So if you do the same thing with XO alcohol, now which bond is anti to that? So this is the bond and this bond is anti to this. So that will migrate if you treat with acid, and this will migrate. So that will give you this bicyclic ketone, okay, and this can be redrawn like this, okay. It is a 5-member ring here and 6-member ring here. So what you have to notice in this is, if you use endo alcohol, you get the corresponding alpha beta unsaturated ketone, but if you use exo alcohol, you get ketone and the double bond moves to the 5-member ring, other ring, okay, no problem. And you can also write it like this, and then now you shine light. So what it will happen? First, the Norris type 1 cleavage to generate the diradical, followed by migration of the double bond. Now this CC bond can rotate, isn't it? This CC bond can rotate, and when you rotate, you can see this diradical will combine to form the corresponding 5-member ring. And if you rotate this by 180 degree, okay, you can go through this and then rotate it by 180 degree and you will get this compound, okay. Hydrogenate the double bond, as I said, you have to shift the double bond here, you do not want the double bond here, you want the double bond here. So first you reduce the double bond, then introduce the double bond. So this is done using Suji-Trost method, where you generate the enol carbonate, enol allyl carbonate, and followed by treatment with palladium acetate, you get the double bond. So once you have the double bond, next is to add the 4 carbon unit in a 1,4 fashion. So take this enone and add this 4 carbon unit, you will get this product. Now as I said, next you have to make this as a good leaving group, generate anion, and then form the third ring. So for that you have to remove the TBDPS, get the alcohol, convert it to good leaving group. So TBDPS can be easily removed if you treat with acetic acid, get the alcohol, convert that into tosylate. So tosylate is a good leaving group. Now you take this compound, treat with lithium hexamethyl disalicide, okay. So it will generate anion and intramolecularly attack the carbon bearing O tosylate in a SN2 fashion, and you introduce the third ring. So what is left now is to remove the ketone. So reduce the ketone to alcohol, convert that into xanthate, sodium hydride, carbon disulfide, methyl iodide, OH will be converted to xanthate, and the xanthate can be reductively cleaved using tributylene hydride and AABN. So to summarize, so if you look at the total synthesis of Uehara and Yoshinari Yamamoto of capnellene, they started with a simple commercially available starting material, that is metacrasa methyl ether. So they did Birch reduction, conjugation, Diels-Hall reaction to get the bicyclic 2,2,2 octenone. Then the key reaction, that is 1,3 acyl shift, was done under photochemical condition to get a 5-member ring and 6-member ring, and later they did functional group transformation to achieve successfully the total synthesis of capnellene. Overall they took about 13 longest linear steps. However, the overall yield is quite good, about 3.7% yield. So with this we have discussed few more total synthesis based on photochemical reaction as the key reaction. We will continue our discussion on synthesis of few more triquinanes, again using photochemical reaction in the next lecture. Okay, thank you.